Okay, so we will start where we left off in the morning, right? So we just finished with the Caesar cipher. Any last questions on that? The Caesar cipher isn't very strong because we only have 26 possible keys. It doesn't take very long to try them all, right? And trying them all is what's called a brute force attack. So we try every single possible key, and when we finally get the one, which will happen on average after 13, then we have it. We can use an encoding table instead to increase the number of keys. So before we were shifting every letter up by a certain number. This time we can shift each letter up by a different number. So we basically scramble the alphabet rather than just shifting it. So like what it looks like for just A to H might be like this, right? And our key then would be 8 numbers long, right? So it would be say 4, 1, 8, 5, etc. So it would essentially be an 8 number long list. That has a lot of different possibilities that it could be for 26 letters. The first is all 26. And then we can multiply that by 25, because it's all that remain when we've removed 1, by 24, all the way times 3 times 2 times 1 is 26 factorial, equals 4 times 10 to the 26 possibilities. That is 4 followed by 26 zeros. That's a vast number. It's gigantic, right? So trying to get this key by brute force is just not feasible. However, while it would take a lot of work to crack by brute force, we could be smart about it. Anyone have any ideas? Sarah? Actually, Sarah, I've heard from you a lot. Velo?
In some languages or some alphabets, some letters are very frequently used, like A, E, R, and T, I think. So if we look at the frequencies of the letters, we can find which one those are.
Excellent. Yeah, so what Velo said is you can look at the frequencies of letters. So like vowels occur a lot more frequency. Francois, is that what you were going to say? Okay. So we'll give you both credit for that one. Sarah, is that what you were going to say too? Yeah. I think we're missing one, so we'll leave that. Yeah, so we can look at the frequencies. So to give us a quick example, all words need vowels. So we can rule out any possible combination that does not put a vowel in every word. So we're going to end up with 5 different encoded letters that are in, one of them at least is in every word, and all other combinations we can rule out. That means that instead, we have 5 different ways to organize what we determine to be the vowels, 21 different ways to organize the rest. This is still a huge number, 6 times 10 to the 21. 6 followed by 21 zeros. But 26 zeros to 21 zeros, that's 5 zeros difference. That is not just the difference of 5, that is a factor of 10 to the power of 5, right? 10 to the power of 5 is 100,000. We have just cut our number of possibilities in 100 thousandths just by making that simple intuition, right? And so yeah, as Velo touched upon, we can use other letter frequencies. E is most common in the English language, right? Followed closely by, I think, A. The last ones, of course, are Q, Z, X, right? We can figure out heuristically which combinations are most likely and narrow it down to just a couple hundred or a couple thousand before we get a message that makes sense, right? So this encoding tables idea is a huge improvement over a Caesar cipher, but unfortunately it's not going to be very secure for very long messages. We can get, however, into a compound cipher. And that depends not only on what letter it is, but also on what position we find that letter in. So it doesn't operate on single characters, it operates on entire strings of characters. An example is doing it up by n on the nth character, right? So A, we shift up by 1, then up by 2, right? And we get this. Make sense? So that's a lot more difficult to figure out because it's not each letter mapping to the same letter every time. We can't use frequencies. What we have as a key now is how much we're shifting each letter by. So in this case, it would be 1, 2, 3, 4, 5, 6, 7, right? that is our key. That's a list of 7. And it doesn't have to be consecutive, right? We can go up 1, down 5, up 18, and that would be our key. This, if we have the key the same length as the message, is called a one-time pad. Right? That key is like a pad. We apply it to the letters. And since it's different for every letter, we cannot possibly figure out what the original message was without the key, right? Because each letter can be shifted up or down by an arbitrary amount. So we could get any message out of this by using a different key. For instance, if we use 142 to encrypt egg to FLA, we can then use the key of 142 to take it back to egg, or a different key, -8, -32, to decrypt it to nog. Right? So we can get 2 different things by using 2 different keys. Without the key, it is impossible mathematically to determine which one or what the original message was. So one-time pads are perfect encryption. We use compound ciphers in HTTPS. It's like a one-time pad, except for very long messages, we end up just repeating it. It's slightly more complicated than that, but that's the basic gist of how HTTPS runs it. We still have one problem, though. Alice and Bob are a world apart, right? We saw that without giving them that initial X, Bob was not able to tell Alice how many siblings he had without Eve noticing. So we need a way to share that initial private key when they're an ocean apart, right? Any ideas on how we might do that? Right? It's very tough to do. And we use an area of math or an algorithm called public key encryption. So that's what Alex was touching on before. That's where we have both a private and a public key. The private key is the one that's shared, the one that they use, and the public key is one that is sent for all of the internet to see, and only using the private keys and information known to Alice or Bob can they get the private keys from it. So we'll take a look at that. It bases itself on the fact that factorizing a large number into 2 large primes is very, very difficult to do, right? So given p equals 29 and q equals 57, what is p times q? We'll call that a. Right? You guys all know how to do that? Getting anything?
1,653.
Pardon?
1,653.
Yeah, so Sarah's getting 1,653, right? Calculating that n takes 2 seconds to do. Now I might ask, what 2 prime numbers multiply to get 2201? That is a much more difficult thing to do. I won't ask you to do it right now. There is a prize if you can do it by the end of the day. Honor system, don't use the internet. I know that's what you're going to ask, right? 2201, it is the product of 2 prime numbers. So those 2 prime numbers, p and q, are what are our private keys, or what we use to generate them. And we can send n over a network, and because it's so difficult to factor this product of n into p and q, we can send n safely without exposing p and q. Edwin? Pardon? Did you cheat?
No, I didn't. We didn't.
How'd you do that?
I used the computer, and the first one I tried was 31, and it worked.
Nice. USB sticker hard hat.
I'm so sorry.
That's okay. Yeah, so you kind of have to try all the prime numbers in order to get it, right? 2201 isn't that big. You saw how huge that key was in our PPK file, right? That key is a very, very large number. We would have to try every single prime number up to it. And remember that the size of a number is the exponent of the number of digits it has, right? So every digit we have in decimal multiplies by 10 and binary multiplies by 2. Alex?
But don't prime numbers become really infrequent? So can't you just divide by the list of all primes?
Yeah, okay, so Alex brought up a good point. Aren't prime numbers relatively infrequent? Can't we divide by the list of all primes? The answer is yes. Prime numbers do get less frequent as the size increases, but they are, as far as we know, they extend to infinity. and they don't get less frequent logarithmically. So the number of prime numbers is about the square root of the number of numbers out there. Actually, not the square root. I've got to look up exactly what it is. It's not log or exponential though. So it's considerably less than exponential. So we multiply the number by 2, and the number of added prime numbers is a lot more than the number that, or like is a lot more relative to what it was before. So multiplying it each time does add a lot. Yeah, like there are a huge number of prime numbers between 1 and, say, a 64-bit binary number. Yeah, so it is very difficult to do, and trying all of them would take a very long time. That's some of the work that's being done on SciNet, is using that supercomputer to actually go and try to factorize large numbers. So far, they've gotten, mostly by mathematical methods, numbers that are a couple 100,000 digits long. That's by mathematical methods. They can't try that out themselves. The point is, for the average Joe on the internet, N is secure. You can't get P and Q from it. So Alice and Bob sends Bob some information with N that allows him to find not quite P and Q, but something similar. So we'll take a look at publickey.xlsx. It's in your shared folder. So this is an Excel demonstration of public key encryption. We won't go through the math right now because it is kind of complicated, and we don't really need to understand the low level of it to be able to use public key encryption. The basic gist of it is we get P and Q. That's what Bob has. He calculates N from that, sends N to Alice. He also calculates an R, and that R is going to be the one that, when multiplied by this M, which is the lowest common multiple of P and Q. Actually, I've got to recalculate M here because that is not correct. So I'm just going to enter 0 and then 1, and that will recalculate everything. Takes a bit of work to calculate it. Okay, yeah, sorry, that is correct. And I'm clicking all over the place where I shouldn't be. So this is the lowest common multiple of them. R is such that R multiplied by M modulus a value they decide upon before, it is mod M, is going to be equal to, forget the exact value. The math, I don't even have it memorized. But Bob is going to calculate an R that's related to our P and our Q and our M. He sends the R and the N to Alice. Everyone is seeing that, right? Alice then chooses an M right here, and she's choosing 56, right? Alice uses Bob's N and Bob's R to calculate a value with her M. She sends that back to Bob. And the mathematics of public key encryption makes it that for Alice to calculate M, given Bob's MC is what she sends. To calculate MC given her M, his N, and his R is relatively straightforward. For Bob to go and take MC and go back using his P and Q to M is relatively straightforward. Since normal users on the internet do not know what P and Q it was that created N, and normal users on the internet do not know what M it was that created MC, given what they are publicly seeing, it is very computationally challenging for them to go ahead and calculate MC. So that's the basis of public key encryption. And if we go on down, actually this should be 4581, so I'll just change that manually. Right, so this is the MC that Alice sends along, and then I'm going to tell it to recalculate everything. And we should get a value in M that Bob calculates when we're done. That is, taking its sweet time. and it's a little glitchy. Yeah, I don't know what it's doing right now, but I'll explain it and get it to work for those who are interested after class. Julian?
Can you run an HTML without the public key?
Pardon?
Can you run the HTML without the public key?
Without the public keys? You can, yeah, and that's what we've been doing, right? The HTTP server we've been using has been unencrypted. So like before I showed you that packet that has all the headers and the plain text HTML, that's what we were sending. Our Python server is also unencrypted. What we'll be doing in a little bit is adding a HTTPS module to our Python, and that will encrypt it, right? So yeah, I've got to figure out why this isn't working, but the gist of it is, given what's public, you can't calculate M. But this M, Alice knows Bob can get it given P and Q, and now M becomes the shared private key. In reality, M would be a very, very big number. We could use that number as a one-time pad to encrypt whatever we need to send back and forth between Alice and Bob. Nicholas?
Isn't that like PGP encryption?
It's very similar to PGP encryption. Yeah, I don't know much of the specifics of that, so I couldn't I couldn't give you like a better answer than it's a similar type of math. But yeah, it does use a similar technology. Other questions? Okay. So we'll head on back here. So that's the basics of public key encryption. We've dealt with encryption. How about authentication? Right? So I'll need 4 different volunteers this time.